as we start, maybe we'll be able to kind of relate it back to everything that we've seen so far. And as we go on, it's going to be, maybe pick out a few pieces and make some few highlights in terms of connections to previous work. So far, we've only had, I think everybody can see my screen, right? Okay. So far we've had only one other work, and it's going to be easy to just overview that one. And this week we're having Yixin Wang talking to us about harnessing geometric signatures and causal representation learning. I believe there's two papers she sent us to possibly check out in relationship to this talk. And the one that we'll be focusing on today is on interventional causal representation learning. So a bit about Yixin. So she's a professor in statistics at the University of Michigan. Her work focuses on Bayesian statistics, machine learning, causal inference, and kind of combinations thereof. She was a postdoc previously with Michael Jordan at UC Berkeley, and then did her PhD at Columbia University with David Bly. And her works received several awards, including an Informs Data Mining Best Paper Award and many others that you can see in the bio that we sent out. So last week, the work that we talked about, I actually just copied this off of Jason's slide from last week, which I think you should feel encouraged to do. If there's helpful slides, just go take a screenshot and copy them. Essentially, we talked about representation learning or dimensionality reduction. There's many names for this thing, as kind of a process of taking something kind of more high dimensional, like an image, and developing a new representation, Z, that might be more useful for reasoning or abstraction is, the main goal of this talk series, thinking about how we can develop representations that are useful for doing generalization in a variety of ways. And often, and kind of the focus of this work, we're going to be thinking about things in terms of a generative model. So instead of starting by thinking about the variables that we see and then asking how to compress them, thinking about a process that actually generates those variables in terms of some latent variable Z that are sampled from some distribution, and then a mixing function, we'll call this G, rendering function. There's also a bunch of names you could think about for this one, that is generating the observed variables from that latent Z. And when we talk about identifiability, we're basically asking whether from the X's that we see, we can figure out this distribution over Z and the mixing function G, maybe up to some ambiguities and determinacies that we don't worry about too much. And this is going to, this generative modeling perspective is going to allow us to kind of prove theoretical results and really match kind of the goal of how we develop representation learning methods on the left-hand side to some process that is supposed to describe where that data is coming from. So this week, we're focused on a specific kind of generative model. And basically, we have this latent distribution Z. We have this mixing function that generates the X's. And in addition to this, well, one is that we're assuming that these Z's are related in terms of a causal model. So there's some distribution over the Z's that are induced by that causal model. And we have, I called them in my work contexts. There's a bunch of different things you could refer to these as: environments, settings, but basically getting data from multiple different data sets. Here, it's just like, say, green data and orange data, and imposing some relationships over how the data is related between those environments, which in the case of interventional causal representation learning is going to be that each environment is essentially generated by picking an intervention target or a set of intervention targets, maybe more generally for that environment. And then describing how that intervention changes the causal model, inducing new distributions over the z's, kind of while keeping this mixing function fixed. So that's all for the introduction, and I'll just finish off by reminding us kind of how we're trying to do questions. Basically, if you have questions during the talk, try to keep those to kind of clarifying questions and ask those either in the chat or raise your hand. And then hopefully we'll have some time at the end, kind of more open-ended discussions. Of course, Yixin, you can specify how you want to take questions if it's a little different than that. And thank you so much for presenting today. So let's get started.
Great, thank you, Chandler. Let me share my screen.
And while you're sharing your screen, let me just remind everybody, it's nice to see faces when you're a presenter. So if at all possible, please
Yeah, I appreciate
turn
that.
your video on.
I appreciate that. And yeah, I mean, it may be a little hard for me to monitor the chat as I talk, but feel free to just shout your question as I'll also pause to take questions. I want this to be as interactive as possible. So I'd rather not get through my talk than getting anybody, getting all of us understand. So I appreciate that. Cool. So thanks for the super nice introduction. And so today I'm going to talk mostly about interventional causal representation learning. And in this particular suite of work, we kind of focus on geometric signatures. And you may not know what I mean by geometric signatures yet. And by no means you will know that if you haven't read the paper. So hold your breath and we're going to tell you what it's about. So this is a joint work with Mike Jordan, who's my postdoc advisor. There's some parts of the techniques sort of came out of a previous paper, and then the interventional causal representation learning paper was with Kartik from Meta, Divyat, and Yasha. I think the latter two are from Mila, and Kartik is with Meta, and Kartik is in the audience today. We're so lucky to have him here. So if you have hard questions, ask him. He did the majority of the work. Okay. So cool. I know Chandler gave a technical introduction of causal representation learning. I want to sort of motivate a little bit how we came about trying to get become interested in causal representation learning problem. And how I got into it was really trying to try to identify independently controllable causal factors, and whatever that means, just like at a very high level. So the canonical example I always go to when I work on causal representation learning is the following. So suppose I start with this data set of unlabeled car images. I have all kinds of cars, and I have this unlabeled car images. And we know that I can fit all kinds of image models, VAEs, deep generate models, everything we can do. We can generate very pretty images. But I also want representations. I want to get representations out of that, and I want them to be semantically meaningful. I know semantically meaningful is very vague, but in this particular example, we have some clear targets. So for example, with a car, I know that I would love for my representation whose first dimension tells me what the identity of the car is, maybe the second dimension tells us what the pitch of the car is, and with the third dimension tells us what the elevation of the car is, and so on and so forth. I want every single dimension of my representation kind of capture one of these independently controllable factor in the sense that I can change my pitch without changing the elevation of my car. I can change the identity of the car without changing the pitch of the car. Like we kind of can independently control all of these factors. And if my representation can do that, then I feel I can generate new cars that has new combinations that I haven't seen before. Right? So this was how we were thinking about it when we try to identify these causal factors. If we call these causal factors, these are factors that generate the structure of the car. So we all have very good intuition about when these representations give us these independent controllable factors. So for example, if I have this representation, which is two-dimensional, where the first dimension is the pitch and second dimension is elevation, then we feel that this gives us semantically meaningful representations. Each of them capture these independently controllable causal factors, whereas the bottom one, where the first dimension is the pitch plus elevation, the second dimension is pitch minus elevation, even though the two representations capture exact same amount of information, we like the second one less because they didn't quite get to the independently controllable causal factors, and it didn't have the structure we wanted. So just at an intuitive level and in the practical level, this is how we think about causal representation learning, at least in the how I think about causal representation learning as a toy example. So why do we care about it? One thing, as I mentioned, is once we were able to identify these latent factors, where each of them correspond to some latent causal factors that's semantically meaningful, then I can consider mix and match. And I can combine, consider new combinations of these causal factors and create new car images, I'd say. All right. And we may also be interested in harder tasks where it may not just be generating static images, but rather I may have latent causal factors that drives a dynamical system. So for example, if I have a bunch of unlabeled ball images that are snapshots of a system of two balls, which are going to interact with each other. So for example, here is a system with two balls, a red ball and a blue ball. And let's say if the red ball is going to have some repulsive force on the blue ball when it's moving to the upper quadrant, and let's say it have some attractive force for the blue ball when it moves to the bottom quadrant, then I am having a system where two balls are interacting with each other. And the hope is if I only have a snapshot of this system, like have a bunch of images or pictures about the system, can I identify this latent system that drives the dynamics of this model? Where, I mean, I don't have time series data, I just have a bunch of snapshots, no timestamp, but I'm hoping that I'm able to get a two-dimensional representation, or actually here a four-dimensional representation where each of these dimension is going to capture one of the coordinates of these two bars. So each bar has two coordinates, and I have a four-dimensional representation. Each of them capture one of these coordinates, and we know that because these two bars interact with each other, so the coordinates, the x coordinate of the one of the bars may affect the x coordinate of the other bar, and y coordinate of the other bar, and so on and so forth. So we may have these latent factors maybe interacting with each other. So if we're like, this is more of a complex causal representation learning task when we have a bunch of ball images about this dynamical system, and we want to be able to identify these latent causal factors that are interacting with each other, and they may be causally connected. So this is a more complicated task because than the cars example, because the pitch and elevation doesn't quite interact with each other, but this will also be something we're interested in. And if you think about, this sounds like a very toy example, but if you think about astronomy, when people are trying to take pictures of what the galaxy look like and how all of these stars interact with each other, this is precisely the task where we want to take from these images and snapshots and measurements of these galaxies and try to understand how many stars are there and how are they interact with each other. And this will be the vision of how causal representation learning may be able to help us if we were able to do this from this models example. And the last example is in biology, is where people would be interested in certain target variables and like clinical outcomes, and they may have some observed features, and people may be interested in how these variables are related, variables and features are related to each other through some latent causal factors. And the goal in here is more like science, as in if you're able to learn these causal representations that drives these observed features and target variables, we take them to our scientist collaborators and see if we can interpret these causal factors. And eventually, if we can interpret and map them to important known biology knowledge, then we may be able to design effective interventions that target these factors and target a particular outcome. Of course, like going all the way to design effective interventions is not something we can do right now. It needs to go through all of these interpretation steps. But what this talk is going to be about is the first step. Like, how do we learn these causal representations to identify these latent causal factors? It's kind of semantically meaningful. So now at this point, I hope I sell you this idea that we're really interested in causal representation learning for these practical purposes. But you may ask, why can't we just fit a deep generate model? And I mean, I know we talked about identifiabilities in the previous talk, but we also have practical reason that we kind of why can't we just fit a deep generate model? So suppose we are just going to fit a variational autoencoder to the data, or or just fit your favorite deep generate models or generated model to the data. We can always just obtain a representation function by looking at, let's say, in the context of variational autoencoder, the posterior mean of these latent variables, and write it down as a function of the data, and this will give us a representation function, so that whenever I'm taking a new data point, for example, an image of the car, I can get the representation of that image of the car. But however, in practice, if we fit VAE multiple times with exact same structure, neural network architecture, or this may also happen with your favorite deep generate models too. If we fit a VAE multiple times in practice, it can actually return multiple representation functions that are equally valid. In the sense that I use the same data set, fit the same VAE twice. One will give you one set of representations, and the other may give you a different set of representation functions. And what do we do with that? And this is what we understand as the non-identifiability of representations in general from deep generate models, where we just fit this model multiple times, exact same setup, we're going to get different answers. And all these answers are viable. They may even achieve the exact same loss, but I may have a non-unique answer. And the downside having this type of non-identifiability is it really challenged the goal which we've laid out earlier, why we want to do causal representation learning. We want to be able to learn these causal factors so that we can take it to our scientific collaborators and ask them to interpret them, to identify what is the biological factor that kind of matches these so that we can design effective interventions. If we constantly get like different representations, how can we even start about interpreting them? But for example, if I have two representations that are, again, equally valid, they just have a little bit of different form, where this first representation is xi3 and xi2 minus xi4, and the other is contains the exact same amount of information, but one of them is the sum, the other one of them is the difference. Both of these representations are valid, but which one should we interpret? And we may end up completely different interpretation from these. Moreover, if we think about the harder task, like how do we uncover the underlying physical system that drives these images we're analyzing, if we can't even settle on a single representation function or identify what these latent causal factors are, like knowing what these variables are, then it doesn't make sense for us to talk about the causal graph. Like the causal graph among non-identified causal factors no longer makes sense. If the variables are not even fixed, they can have multiple answers only under very stringent conditions when we can rationally talk about the graph, the connections. If in general, the causal connections, the causal effect between unidentified variables kind of doesn't make sense in general. And of course, they all prevent the downstream design of targeted interventions for latent causal factors, because we just don't even know what these latent causal factors are, and there are just so many equally valid answers. So I hope at this point, I convinced you that we kind of really care about identifiability from a practical purpose, like for the causal representation learning to really help us down the road for practical purposes. Like we we want to care about identifiability. Like it's not just something, a theoretical construct that we're intrinsically interested in, but rather this bears practical consequences. So now that I'm on this topic of identifiability, I want to clarify what exactly do I mean by identification in this particular context. So in this suite of work, in terms of interventional causal representational learning, we're interested in identification of latent causal factors in the sense that suppose my data is generated by some true latent causal factors, like suppose I have the ground truth, where we have the same structure as what Chandler has described. Zi with my latent through some mixing function G, it's going to map to some data Xi, and this mixing function is deterministic, which is important. Now we want to have an algorithm that takes in, or just think about it as a mapping, takes in my data and output two functions, G hat and H hat, where we want the G hat, which is the estimate of this mixing function, to exactly coincide with the true mixing function. And I want my H hat, which is my representation function that takes in my data and produces a representation. I want my representation, which is obtained by H hat of Xi, is going to exactly coincide with the true causal factor that generate the data. So they need to be exactly the same. And this is what we mean by identification of latent causal factors. I think this is a good time to pause. This is kind of important point. And I'm happy to take if there's any questions up to this point. Seems like we're all fine, right? Oh, great. Yeah, Elliot, please.
So yeah, quick clarifying question. Like, is it not the case here that G hat and H hat are always just going to be inverse of each other? Or is there something more complicated than that?
The G hat and they will, I mean, they will satisfy a reconstruction identity, but right, yeah.
But they don't actually have to be literally one function inversed. It could be more flexible than that.
No, it will have to be inverse. We didn't write it that way because like in the general, it's a little complicated because in general, we are reducing high dimensional data into low dimensional representations. So if you write down the G function, it's a mapping from some low dimensional, say our low dimensional space to a high dimensional space. It's a little hard to exactly talk about inverse, but you can kind of think about them this way, because eventually we need to assume that G is some form of injective on the support of the data. So there is a bit of a technicality to say what exactly do we mean by inverse, but the intuition is exactly right. We want them to one exactly encode, and then the other exactly decode that. Yes.
Okay, thanks.
Cool. So this is how we think about identification. So now the rest of the question is, how do we get there? And how does interventional data is going to help us? And if we don't have interventional data, how is there any signature from the data that can help us? So we got into thinking about this. I mean, there is a huge literature on talking about establishing identifiability for deep generated models. And one of the key assumptions people make, which makes a lot of sense, is people often assume that their latent causal factors they want to identify are statistically independent. So that is to say that, like, if you write down their distribution of these latent variables, they're actually like jointly independent. So there are a lot of works that can do this in the sense of we have independent component analysis, ICA, nonlinear ICA types of work. There's also variational autoencoders where people introduce independent latents and auxiliary variables and Gaussian mixture priors and all of these. A lot of cases people want to assume they have statistically independent latent causal factors. So this could be, importantly, this is different from what we understand as independently controllable factors, where we were talking about changing the pitch of the car will not change the elevation of the car, and we can change the identity of the car without changing the elevation of the car, so on and so forth. So there are different notions of independence, but there are a lot of work in the space about talking about independent latent factors. But in examples we consider, most of the latent factors are not statistically independent. Even though we want them to be independently controllable, they could also be just correlated because they share some unobserved common cause. They can be correlated, or even like in the Ball's example I gave, they can be causally connected. Like it does not make sense to talk about them as independence. So this will be our focus today, as in, suppose my latent causal factors are correlated or even causally connected. What assumptions, what information can help us identify correlated latent causal factors and even causally connected latent causal factors? And as it turns out, the geometric signature, in particular, we're going to talk about the support of the latent variables, is going to be very useful, turns out surprisingly, to help us identify them, even though these latent factors are correlated. And they could even further help us when we have interventional data, and the geometric signature of the support of these latent variables can also give us a lot of information about that, which will be what we're going to talk about in the rest of the talk. So let's jump right in. So let's start with the simpler case, or let's not go all the way to the harder case where we have latent variables that are causally connected. Suppose we're working with a simpler case, like think about the cars example, if we only have just correlated latent causal factors. So if I write it down in a graph, I'm going to have all these high-dimensional observed variables driven by some latent causal factors, Z1 up to ZD, and they're correlated in the sense that they're all driven by some unobserved common cause that induces correlation among them. All right. So importantly, these latent causal factors don't causally affect each other, to reflect this situation that we can change the pitch of the car without changing the elevation of the car. They're all independently controllable, so they don't causally affect each other, but they can be correlated because they can share some unobserved common factors that induces their correlation. So our goal is we're going to, even though they're correlated, we still want to identify the correlating latent factors Z1 up to ZD. But we're going to start with simpler case where they're not causally connected, these latent factors, but they're just correlated. So how do we deal with this? The key observation we had is it turns out that latent causal factors just often have independent support. So this actually came out of, we went back to the disentanglement data set, disentanglement lib, and we have all of these labeled features from all of these images, including these cars ones as cars or balls and all of these data sets. And we're just asking, like, what features or what characteristics do these like ground truth latent causal factors really have? And the first thing we did is to just make a scatter plot. And this turns out to be a lot of what a lot of the scatter plot will look like. And we basically give this a name of independent support. And here's what we mean. So what we mean by independent support is, suppose I have two factors, orientation and scale, then these two factors have independent support if no matter what the value of the scale is, the support of orientation, which is the possible values the orientation can take, does not change as I change the value of the scale. So it means whenever scale is equal to 0.5 here, the orientation can take all possible values from 0 to 6. If I shift the scale to be equal to 0.6, my orientation can still take the same set of values from 0 to 6, and so on and so forth. So whenever we have this type of properties in the sense that the support of one variable does not depend on the value of the other variable. We call it independent support. And visually, so these three examples are all ones, the scatter plots of factors that satisfy independent support, where for each variable in this pair, their support does not change no matter how the other variable changes. On the other hand, these are three examples where the independent support is violated, in the sense that suppose we have this one factor which we call entangle one. When entangle one is equal to 250, and here the entangle two can only take values up to around 150, from 0 to 150. Whereas if I change my entangle value one to be entangle one's value to 1500, then the possible values that entangle two can take increases above and goes above 150. So the possible values that the other factor can take will, in this case, will depend on the values of the other factor. So when we have this type of support independence, as in the support of one factor depends on the value of the other factor, this is a violation of independent support. And intuitively, visually, what you will see is if two factors, if you make a scatter plot, they kind of occupy a rectangular region, then they satisfy independent support condition. And if they don't occupy a rectangular region, they have this kind of weird shapes, they don't satisfy independent support. So it came first as an empirical observation that it turns out a lot of these factors that we really aim for have this independent support condition, which we can rigorously write down in terms of this factorization. See, the support of this joint is the product that supported each latent variables. And it turns out it does have causal roots. Like, turns out if we are willing to make a positivity condition, which could be a strong condition, but it's a standard condition in causal inference, but it could be strong. But if we're willing to make a positivity condition under about the latent variable C, the latent unobserved common cause C, then we can show that no causal connections, the absence of causal connections among these latent variables, latent causal factors, will imply that they must have independent support. So importantly, this doesn't go the other way around. It's a necessary but insufficient condition. I say that the absence of causal connections among these latent variables will imply independent support. So what this means is if I observe the support of my latent variables look like this, we know that something is going off. They're not like the causal factors where I wanted. But if I observe the support really satisfied independent support condition, we have more confidence, even though this cannot imply that they do not have causal connections among them. So what we did was, let's see if it works. So we developed
Can I ask a quick question?
Yes.
You invited people to interrupt.
Yes,
so
please. Yeah, appreciate it.
If I can look at these scatter plots that you shared,
Mhm.
and if you would go back to the previous slide, just so we can look at the positivity condition really quickly. For all of the figures in the right column, is that to say that they violate the positivity condition, even though they are maybe correlated only at a degree of 0.2 or 0.3? Is it the case that the fact that they violate independent support here means that in some sense they're lacking that positivity?
So here the correlation is about statistical independence. So this is calculating the statistical correlation between these latent causal factors. So this is trying to indicate that
right. But I mean, I'm wondering if does that statistical independence or dependence, is that kind of reflecting at all the lack of positivity, in the sense that, like, if one of the variables is too much of a proxy of C, would this show up as the signature on the right hand side?
Right. So it goes one way but not the other way. So if we have non-independent support, then they must be correlated. So it's impossible to be independent and their support look this way. So independent variables must have independent support. So independent support is a strictly weaker condition than independent statistical independence. So it wouldn't be surprising to see like correlation, high correlation with these violations of independent support. However, there's a middle ground there because independent support is weaker than statistical independence. So it is possible to be correlated and satisfy independent support. So, and that's the middle ground we're aiming for here, as in they're not statistically independent, but it's still possible for them to satisfy independent support. Yes.
Right. But maybe another way of asking this question though is like, what do you think is going wrong with the right-hand column? Like, why are they violating independent support?
Oh, this is because they are the factors are causally connected. I mean, this is a simulated example. We actually kind of simulated causal connections.
Oh, I see.
Causally connected. Yeah.
Gotcha. Okay.
Yeah. But this is great clarifying. It's important that independent support is a consequence of statistical independence, but not the other way around. So we're kind of striving in a similar direction, but kind of find the middle ground where there's still something weaker to be satisfied, but they're not independent. Yes, Jason.
I mean, I really like the observation that you know the theorem that you guys have makes, but in some ways I kind of almost interpret it the opposite way, which is that like this should make us more skeptical of positivity rather than something that, like, do we have examples of random variables that have independent support but dependence that are not synthetic?
Right.
You know? So
for the cars example is one, right? I could totally have these features all not causally affect each other, but they just happen to be correlated in a data set.
I see. Yeah.
Like I can just go ahead and subsample a particular car's data set where the pitch happens to be correlated with elevation, which happens to be correlated with their identity, even though none of them cause each other. I can totally manipulate everything.
Okay.
Right. Yeah. I mean, this is all just to say statistical independence is a little too much to ask for.
Yeah.
Like if we just grab a data set from the street, it's very unlikely that these latent factors, even though as much as we want it, they're going to be exactly statistical independent.
Yes, I agree. I totally agree with that. It's more just that like independence, like when I've tried to construct distributions that are correlate, like highly dependent but have independent supports, like you can do it. You can do like nice beta distributions that have nice correlations, but whenever I've tried to do it, I found the distributions end up being kind of contrived in a way, you know, like you have to sort of force compact support.
But I think, I mean, it will be hard to construct if we want them to be highly dependent, but that we want them to be independent support. Here, they don't necessarily need to be highly dependent, the latent causal factors, in the sense that the pitch doesn't need to be highly dependent on the elevation or other things. So when we go to the causally connected factors, then we'll get to these situations where these causal factors are causally connected, but then that's why we need interventions. Basically, what interventions do is to recover these causal connected situations back to here, so that the intervention will break these connections. So this will become a signature that we can make use of. That makes sense. Yes. Danya, please.
Sorry for one more quick question, Yixin. And maybe you'll get to this, but I'm just kind of curious, even if there is a causal connection between, let's say, Z1 and Z2, but if Z2 was also affected by some Gaussian noise or something that made it so that it did kind of span its full range of values, are there situations like this where you still get independent support? Or when maybe you're making interventions, but they're soft interventions?
Right. So, I mean, there is a difference between whether independent support hold and whether that will give us anything. So the Gaussian example is a case where independent support, like theoretically will hold, but it will not be able to give us anything, because no matter whether I intervene or not, like the support will be from -infinity to a positive infinity. So you actually alluded to one important point where in this suite of work, if we're looking at support, we can only look at bounded latent variables. And that's where the support kind of shows up. I can see when the latent variables is bounded, I can see the support changes or support violates something. If the latent variables are just unbounded, like they are going to be minus infinity to positive infinity always, then like they satisfy it, but so what? Like I don't get anything from it, right?
Gotcha.
Yeah. Cool. Great. So we were talking about independent support, and I mean this slide is just to show you that like it's, even though it come out of as an empirical observation, it has causal roots, as in this is the implication. So what we first did is just do it empirically. We come up with some naive score where we literally assess the distance between sets of these supports, which is the most naive thing you can do, wouldn't do any trick, and put it as a regularizer to see that if I enforce independent support in just fitting a deep general model, does it help at all? Is this come from empirical observation? And turns out it does. Even though a priori there's no reason, it's just a necessary but insufficient condition, but it does help. So we ran some experiments, and as it turns out, it can separate out these in these disentanglement benchmark, disentangled and entangled observations quite well, where these ones are ones with lower, we call independent support score, IOS score, and these are higher IOS score. They can separate these two cars quite well, and way better. This is complete unsupervised, and it's way better than total correlation of Wasserstein dependency, which is kind of a straw man because they look at statistical independence. And so this wouldn't be surprising. And if we use it as a regularizer, just adding this to any of our deep general models, it turns out we can further improve the disentanglement benchmark, disentanglement performance much better. Where this interventional robustness score is assessing faithfulness to the ground truth latent causal factors. And we also assess like what exactly is doing the job here. And it's precisely because of this regularizer. As we increase the strength of this regularization, this performance disentanglement improves. So like we kind of get closer and closer to our latent causal factors. So this is all just to say, we have some empirical observations and it works. And we're going to talk about the theory in a minute. Yes. Please, there's a question.
Hi, yeah, I just have a quick question. So in these examples that we're just showing, are we guaranteed to have like positivity? Because that was like the necessary condition there.
I mean, positivity will be an assumption we need to make about the latent variables, and it will have to rely on domain knowledge and to understand whether we think that's possible or not. So for example, if these latent factors we feel as in the cars example, we have like pitch and elevation and identity, then we feel that it's, if we have a large enough data set, then positivity probably holds, in the sense that for all kinds of pitches, they may be paired with all possible elevation, paired with all possible identities, or like nearly all possible identities. So these are cases where it can plausibly hold. But if you are in more fine-grained cases where, say, if I have just gene expressions where every single latent variable is a gene expression, then this is unlikely for positivity to hold because they just genuinely live on a low-dimensional manifold, and it's impossible to satisfy positivity. So this will depend, like assessing positivity will come from domain knowledge and our understanding, like our guess of what type of latent causal factor are we aiming for. The answer is it.
I see. Just to clarify more, because I'm referring to the theorem that you were describing. So because the necessary assumption was like positivity, and then you said that if we observe like no independence of support under positivity, we can deduce that like there is a causal relationship between variables. But how can we differentiate? Like if I just see like no independent support. So there might be two results, right?
Right.
One is like positivity doesn't hold, and the other is okay.
In that case, we just cannot from that theorem. This will like why they will violate independent support will need to come from other sources of information.
I see. Thanks.
Cool.
I also have a question.
Yes,
before we
please.
go on. You mentioned you need the like random variables to be bounded.
Yes.
And then I was thinking, maybe this was mentioned last time too, like if you allow kind of like any nonlinear transformation, like kind of pointwise of a variable, you can go from something bounded to something unbounded, like a sigmoid,
Right.
or
Yes.
like inverse of that.
Yes.
So are you like somehow choosing something canonical, like it has to be truncated Gaussian, or how do you
Right.
get
So
rid
this
of
is a
that
good question.
indeterminacy?
And right, this is a great question. We're gonna get to it. And this is why in our theorem, we first need some other assumptions like polynomial, injective polynomial mixing to get us to linear identification first. And
Great, thank
once,
you.
so to achieve the cases that you described, we need nonlinear mapping to map any arbitrary support into independent support to be a bounded ones. If we only restrict linear mapping, then we can't. And this is why we need some other tools to get us to linear identification, and the support will like break the linear identification and get us identification. Yes,
Thanks.
that's great. Cool. So now we've seen this independent support and it seems to work, but like how does it help us with causal representation learning? How can it identify correlated latents? So this is a result from, as a prelude to the interventional causal representation learning. So if we only have observational data, and we can show that under polynomial decoder, in fact, injective polynomial decoder, and bounded true latent causal factors, then we can show that the pairwise independent support condition, in particular, we just need pairwise independent support, can provably identify latent causal factors up to permutation, shift, and scaling. So the intuition was exactly revealed by Chandra's question, where we use polynomial decoder to get to linear identification, and the pairwise independent support turns out to be able to just break linear identification and give us identification. And I mean, the most important intuition to think about why independent support will help is, as I said, the visualization, the way to think about independent support is if I make a scatter plot of two variables, it's kind of occupy a rectangular space. Right, and the core hardness of having linear identification is they're rotation invariant. Like I can rotate things and without changing their distributions. But this will actually, the rotation invariance doesn't go well with independent support, in the sense of if I rotate a rectangular some way, it will no longer be rectangular anymore. This is how we get identification. Like if you have linear identifiability and with independent support, they can exactly give you identification of individual latent variables because of this. When you rotate a rectangle, they're no longer going to be rectangle. So if I restrict myself to be a rectangle, then I'm going to be able to find that one. All right. So as formally,
Yixin, just a quick clarification. You said that you use interventions to allow for dependencies among the latent variables. Are you gonna explain that, or is that?
Yeah, I will go to that. I'm here in the base case where we're in. I want to explain if we don't have causal connections. Once we understand this, why intervention is going to help is hopefully obvious. So just formally writing it down, if we have the generating process, the whole setup is same as Johnny's talk, and if we have a decoder, we want to have encoder, and we have a representation, then what we're going to do is we need to solve a reconstruction identity to make sure that autoencoding really recovers the truth. And we further restrict independent support constraint on the latent variables, where these latent variables support is output by the encoding function. Then we can show that the latent variables is going to be able to identify, coincide with the true ones up to permutation, scaling, and shifting. All right. So now we're finally going to get to the meat, or we eventually be able to do. So what if we're dealing with a harder case when things are causally connected? And this is where interventional data plus this independent support is here to help. And kind of by definition, interventions mutilates the arrow, like remove the arrow between the intervened variables and its parents. So when we break this arrow, we kind of like start with the case when these latent variables are causally connected, but now we intervene them. So we'll remove this arrow. We kind of reduce this harder situation of causally connected latent factors to the easier situation we just talked about, where these latent variables don't causally connect to each other, but they're just correlated, but even so, just some subset of them. And this is why interventional data is going to help us leverage the independent support condition to be able to identify these latent factors intuitively. So in this sense, we're going to use interventional data together with independent support to be able to handle both perfect interventions and some imperfect interventions, but we'll need like only particular type of imperfect interventions where we'll preserve independent support, even though it's an imperfect interventions. And we're going to be able to show that we can identify these latent causal factors with sufficiently many interventions and then identify their causal graph. But broadly, this is intuition. Like, we understand that independent support can help us find these latent causal identify these latent causal factors without causal connections. Then when there is causal connections, we use interventions to break them, and we can go back to our base case. All right. So more formally, we will need to work with multi-domain interventional data or multi-environment data or multi-context, whatever, where every single domain comes from some interventions. And depending on what type of intervention it is, we may be able to do things or we may not be able to do things. So importantly, we do not know which latent causal factors were intervened on. We only know that some factors were intervened. And here we're restricting ourselves to single node interventions. And as it turns out, the geometric signatures will reveal latent causal factors. And I hope this picture will kind of give us intuition. So suppose without intervention, my latent variables are causally connected. They may not satisfy independent support whatsoever. But once I intervene, let's say I start with a do intervention to set the latent variable Z2 to be this particular value, then immediately the pairwise support of these two random variables gets squeezed down into this line. And I have independent support in the sense that no matter what value Z1 is taking, the Z2 can only take this one particular value. And Z2 can only take this particular value, and its corresponding support of Z1 will be the whole real line, right? So this is how intervention geometrically is giving us signatures so that we can leverage to identify which is Z1 and which is Z2. Similarly, if we have imperfect interventions, and only a subset of them that can induce independent support, then we can go back to user independent support ones. So the final one is the case that if we do imperfect interventions, but it cannot give us independent support, then we cannot do it. As of this suite of techniques, we cannot do it. So more formally, we'll be able to handle do interventions where we solve the same reconstruction identity subject to the constraint that some dimension of the latent variable gets set to one particular unknown value, then we'll be able to identify these intervened latent subject to injective polynomial and non-empty interior. If we have multiple do interventions, then we may be able to get away with our injective polynomial assumption to work with general diffeomorphism. And we can show that if we have only diffeomorphism, non-injective mixing function, and the number of interventions is large enough, then we may be able to approximately identify these intervened latents component-wise. And finally, if we work with perfect or imperfect interventions that satisfy pairwise independent support, then we'll be able to, in similar suite of assumptions, inject a polynomial non-empty interior and support independence, and we can get block affine identification. All right. So, and broadly, the intuition here, as I said, is both perfect, hard, or soft interventions on the latent will always give us independent support because they're breaking the connections. If we're working with imperfect interventions and we're working with a specific class that it also gives independent support, then we will be able to make use of independent support to help us get identification. And the algorithm is easy. We could just go ahead and take a pre-trained representation and learn a linear transformation of So if we think the representation is already linearly identifiable, then what we can do is a post hoc adjustment where you try to learn a linear transformation of the representation such that at least two variables satisfy independent support in the interventional data. All right. So we did this with the Boz example as it started off. And as we increase the number of intervention distributions, see that this is MCC score, mean correlation coefficient, kind of assess faithfulness to the true causal factors. We're able to identify the true latent causal factors without compromising reconstruction identity quality. And in our full paper, we had a lot of other results, which is a summary. We handle in general with observational data, with correlated factors, or the more general causally connected latents, but with interventions, we're able to get different suite of identification results through this type of study of the support. I want to give a quick plug for the new work where we have deviated from support independence to support invariance. And what we gain from that is all of these results I talked about in this particular talk is going to focus on single node interventions. Whereas once we go generalize ourselves from support independence to support invariance, we'll be able to handle general multi-node imperfect interventions and in even more general multi-domain situations where we don't even have a single DAG. But I won't be able to talk about this, and you can welcome to invite my co-author to give another talk about this. So I want to close my talk with some quick takeaways. I hope I motivate the practical relevance of causal representation learning, where we try to aim to identify latent causal factors from unlabeled observational interventional data. And what this talk is focused on is we want to look at if the latent causal factors are not statistically independent, they're just correlated or even causally connected, how to identify them. And it turns out the simple geometric signature of independent support in general, looking at the support of the data, which unfortunately involves no statistics in there, but the support of the data turns out to contain a lot of information that can help us identify latent causal factors from observational interventional data. And the first two papers are where the independent support kind of focused on, and I didn't talk about the last paper, but this is a new work. We were able to go from support independence to support invariance, which I hope to have another opportunity to talk about with my co-authors. All right, cool. I guess with that, I'll close my talk. Thank you.
Thanks so much.
Awesome.
I'll
Thank
thank
you,
the
Yixin.
speaker. Yeah, so up to Yixin, how much longer you want to stay around? We're at time, so people,
I mean,
if you
I
have
have
stuff
time
to get to, feel free to go.
Yeah.
But
I have time, so
generally,
feel free
yeah.
to ask questions. I'm happy to take them. And Kartik is also here, so I don't know. Can Kartik say something?
Yeah. I mean, yeah, I'm happy to take any questions or discussion. Yeah.
I would love a little bit more intuition on different aspects of the interventional CRL paper. I'm wondering if you could go back to some of those slides, Yixin.
Sure. This one.
Maybe your nice slide with the pictures where you had the 4 different boxes. Yeah, exactly. This one. Perfect.
Yes.
You mentioned that when you had imperfect interventions and it was still imperfect single node interventions.
Yeah,
you mentioned block. Okay, perfect. I have 2 questions. My first is, you mentioned block identification being possible. I was curious why blocks and not permutation in that scenario.
Kartik, do you want to take that one?
I mean, it's actually possible to extend it to even permutations. Just requires a bit of a hassle. So happy to talk about it. I mean, it just makes things messy, to be honest, from an algorithmic point of view. It was just for the cleanliness of stating the result that I intended to get the minimal thing. And after that, it's a bunch of searches, which I did not want to make the thing more complicated than needed. But it is possible. Yeah.
Okay, that sounds good. And then, so if we were to take the, let's say, imperfect intervention, or even the do intervention scenarios, can you offer a little bit of geometric intuition perhaps on sort of why does the signature not help us if we were to have multi-node intervention? So what kind of breaks when we start considering multi-nodes?
So should I or Yixin?
Yeah, go ahead.
This is
Go
for
ahead.
either of you. This is or
Yeah,
both of you.
please
You
go
can take
ahead.
turns.
I'll defer all the hard questions to you.
I mean, so the thing is, it's not. So here is the thing. So with the way I was thinking about imperfect interventions in this case was that let's imagine the picture that Yixin has on the left-hand side where Z1 and Z2 are connected, and the shape of the support, the joint support, has this complicated looking thing, right? And with an imperfect intervention, the intention is that the strength that the parent exerts on the child reduces in a way that the range of values that the child is taking at least gets relaxed to the extent that now the range of values are not constrained. You could imagine scenarios that would be possible in a multi-node setting too, but that might start to look a bit contrived. But I think at least for a pairs of variables or like single node thing, you can imagine that at least the strength that the parent exerts on the child, and then you can have this nicer. I'm saying that you should not think of this support independence as to happen in an ideal way that you get a rectangle, but the region should expand and it should start looking like that. And that seems more feasible in the case of a single node intervention. When you go to multi-node interventions, what we realize, which is in this other paper, is that there is somewhat of a more natural signature, which is support or distributional invariance, which is when you intervene on something, that variable and all of the children may get influenced and their distributions may change, but everything other than those will not change. And that is a first level signature that is currently not used, and which is what we use. So, because that would even be true for multi-node interventions. If you do multiple interventions, the union of things that get impacted are gonna undergo a support variance or distributional variance, whatever the signature be. We look at different signatures in the paper. And again, the remaining nodes that are not impacted by the multi-node interventions, which would be the union, the complement of whatever was impacted, they have the invariance. So what we are trying to show in the other work would be that at least could you separate these two blocks out? And the answer turns out under different relaxations and all of that to be yes. So that's how we see these two things. So this is probably more natural for single node. That's a more natural signature for multi-node. It will only time will tell which is actually a more useful one. But yeah, these are initial attempts. Yeah.
Sort of maybe basic question. The example on the right of the sort of failure case, independence intervention without independent support. It seems like that's probably like the minimal, like if you want to try to maximize independence of support, that orientation is probably it. If I imagine all possible rotations and I want to find the rotation that maximizes the independence of support, that orientation that you've got there is probably it.
Yeah, it's almost there, but it's not fully there, if that's what you mean, right? In that sense, or
I mean it more in like if I'm choosing which rotation of this box like maximizes the independence of support in some sense, even though it's not independent support, it's like the rotation that maximizes.
You could surely draw worse failure cases if that's what you mean. Yeah. I mean, you could just draw a different square and
I mean, clearly you'd need an additional assumption, but it does seem like there's probably a weaker version that is slightly more general. I don't know. It's hard to say what that is, but that's almost an example of it.
Yeah, I mean, largely speaking, I think there is a somewhat of a symmetrization of the volume argument, like across the marginals. I don't know how to state it, but that's where maybe a more general setting or a result lies. I don't have a very clear way to articulate it, but yeah, I mean, yeah. Yixin, you may want to add something to that if you.
No, I think, yeah, like I feel like certain form of relaxation of independent support, like even approximately independent support, maybe possible. I guess this is probably what this picture is getting at. And we could have drawn a worse failure case that like more drastically validated. I think what will be tricky is to figure out what exactly is the relaxation that's more practically useful, and it's probably like a more case-by-case argument to make things a little messy. So I guess in practice, we don't exactly enforce independent support, but kind of use it as a regularizer or kind of minimize the independent support score. It kind of implicitly did some approximation in this algorithm. Yeah, kind of hand wavy, we kind of did it. But yeah, because this is all like identification argument, and we're already living in the ideal world that we have infinite data, like injected polynomial, like we were making all these assumptions. So we'll stick with.
So just on the note, since you're discussing the like how practical all this is, one thing, maybe one paper that did not come up, but I actually like that paper quite a lot, is from Pascal Vincent and Diane Bouchacott and others at FAIR, where they basically are using this independent support idea and are applying it at in different settings. And you like I when I first time read it, I found it a bit surprising to, even though I have written a paper on it now, that like I had also initially found it a bit surprising that empirically it actually seems to be quite useful. So I can share the paper in chat if you don't know which one I'm talking about, but it's a good paper to show the empirical promise of it if there is some disbelief still. So yeah.
Yeah, that's a great paper to bring up. I should just add to my talk in future. Yeah, and please, send it to the chat.
Please do share it. That sounds great.
Yeah, it's a large-scale empirical study of this, and they actually independently came up with this without knowing.
Right. Yeah,
Okay.
I told them about your paper, so yeah.
Right.
Fun.
It was
Uh,
them to think of this. Yeah.
all right. Yeah, they came up with it independently, absolutely. So which is kind of nice because
Yeah.
is actual.
And they did a way better empirical studies than I did. So.
Yeah, I put the paper in the chat, and yeah, I think there is also a nice repo associated. So feel free to check that out if you're actually trying to push and break and play around just with independent support as a penalty in standard disentanglement lib datasets to get started on all of this.
I think I don't see a paper. Are you sure you posted it in the chat to everybody?
Oh, I think I just messaged accidentally just to Chandler, which is a weird thing that I did. And all right, I'm gonna change that. Chandler, you better read that paper.
I got it twice, so now I really have to look at it.
Yeah, exactly. Well, now I've shared it with everybody, I hope, right?
Yes.
Yeah.
All right.
Okay.
Are there any other questions, or should we leave it at that?
Yeah,
that sounds good. Thank you so much, Yixin. That was a fantastic.
No, thank you for having me.